Hello, Dr. B here, and let's talk about measurement, uncertainty, and significant figures. It matters whether you're dealing with an analog system or a digital system. Okay, somebody's taking a volume measurement. What would you record as the volume? Well, there's a lot of things at play here. First of all, this person is doing it wisely. They are lining up their eye parallel to the bottom of the meniscus. This prevents parallax. You can get an inaccurate reading if you're too high or too low. It also is in agreement with the convention that for things that have a meniscus, let's measure it from the bottom of it. And what should we record? Well, the number they recorded was 32.0 plus or minus zero point 0.5 mLs. There's a lot of information here. Let's go through it. It's around 32, clearly, but they didn't just say 32, they said 32.0. I guess we should estimate a digit between graduations. And I guess the accuracy is going to only be within half of that estimated digit. On the other hand, here, it's 126.4 pounds, and what's written down is 126.4 plus or minus zero point 0.1 pounds. Well, writing it down straightforward enough, and I guess here we have a sort of inherently higher accuracy. Since we're not estimating, we will assume that this balance is within the lowest graduation of error, so plus or minus a tenth of a pound in this case. Therefore, for analog readings with graduations, estimate between the graduations, and the uncertainty will be half that estimate. But for a digital system, just write it down, and the uncertainty will be equal to the lowest graduation, in this case, a tenth of a pound. Don't forget your units. Why do we need to line up that meniscus? It should be pretty clear that you're going to get an inaccurate reading if you're too high or too low. This is called parallax. Some devices, and these are kind of obsolete now, but they were so cool, would minimize parallax by putting a little mirror underneath it. So you looked at it from the side, you'd see a little black reflection line there. But if you're lined up perfectly, it's hidden by the line itself, and it helps you to minimize parallax. Okay, let's talk about significant figures by example. The number 32 is said to have two numbers that really matter, that are significant. Why? Well, I don't know how you're going to represent 32 without using both the 3 and the 2. Or you could simply say, skipping over that, you can just say that non-zero numbers are always significant. How about this one? We got some zeros there. Well, since we can say this is 3.23 times 10 to the minus 2, we are going to say we always dump those leading zeros. This only has 3 significant figures. They're never significant. Always dump the leading ones. You can't represent this scientifically or otherwise without those 2 zeros, 3.004 times 10 to the 0. But there you go. It's all 4 of them are needed, so keep the sandwich zeros. 300 versus 300 with a decimal place is considered by scientists to be two different numbers. This one has, well, technically in IB language, we say 1 here, but if you read the IB textbooks, you'll say it's unspecified, which might be a better answer, so you might want to make a note of that for International Baccalaureate Chemistry. Most other textbooks will say that it only has 1 because we don't know if they were counting by hundreds or whatever. So that has 1 significant figure depending on which course you're taking. Remember, IB, say it's unspecified. And this one here, since there's a decimal place there, hope it's not a period in a sentence, but there's a decimal place there, so that will be definitely all those 2 numbers were actually measured. They were 300 cows or something like that, and they are considered to be all significant. So keep it if there's a decimal place. Keep the trailing ones if there's a decimal place. Applying those rules, we're going to keep these central ones and keep the trailing one because of the decimal place, giving us 5 there. Try this one for mastery. Well, first one we better dump it. Second one, we always keep it. Third one, we keep it because there is a decimal place, therefore 5 significant figures. What if we wanted to say 2.25, but we can only use 2 significant figures? Should we go 2.2, 2.3? Somebody a long time ago said, go up. So it's 2.3. How about adding and subtracting? If we're adding these 2 numbers, annoyingly, the rule is to keep the fewest number of decimal places. Since this is only accurate to the 10th, the raw number is 7.46, so it can only be accurate to the 10th. I'm going to say 7.5. Therefore, significant figures is based on decimal places when adding and subtracting. Here we have two numbers, each with 3 significant figures, and we're dividing them. The rule for multiplying and dividing is to keep the fewest number of, that's right, significant figures. 3 in each case. So the answer is 2, but is it 2, or can we say it more precisely? I would use 3 significant figures, and therefore it's 2.00. Some things have infinite numbers of significant figures, like counting, or rules that are just known to be completely accurate. For example, 12 inches is exactly a foot. Should you round as you go if you're doing like some PEMDAS situation, adding and multiplying and stuff? The best thing to do is to store it in your calculator and only round at the end. If you can't do that, and that oftentimes happens, carry what they call a guard digit. Have at least one extra significant figure. Will that give you the exact same answer? Just about. How many extra digits should you carry along? At least one. More is okay. Combinations is never taught in any textbook, but you can find it if you search hard enough online. In this particular case, we are both adding and we are multiplying. We simply get the raw number with plenty of accuracy and then apply the more stringent rule. Here it looks like if by adding we're going to be only accurate to 2 decimal places, and by multiplying there's only 2 significant figures. So the raw number is 268.653. The more stringent rule would be 2 significant figures. So we have to say 2.7 times 10 to the first, or 270 without a decimal place. That is measurement, uncertainty, and significant figures.